So the last section of this digital communication course is error control codes. In that we will learn linear block codes, cyclic codes, and convolutional codes. So let's start. Terminal connectivity. You all know that we can connect transmitter and receiver in these three different ways based on the transmission. In simplex, transmission is only one direction, like shown in figure A. Transmission is from A to B only. That means only B can receive transmission from A, but cannot transmit anything to A. Half duplex transmission can be either direction, but not simultaneously, like in figure B. Either A or B can transmit at at a given time. Means both cannot transmit simultaneously or at the same time. Full duplex transmission can be done in both directions simultaneously. Means A and B can transmit towards each other at the same time. Then we have types of error control. We have three types of error control discussed here: error detection and retransmission, power error correction, and ARQ, automatic repeat request. In this mode, the receiver detects errors in the received data but cannot correct them. Instead, it asks the transmitter to retransmit error near part of the data sequence. This method requires a return link. So this error detection and retransmission, uh, it's not correction, it's only detection and retransmission. In that, a pre-specified error control can detect the error, means it has the capability to determine that whether the received data is in error or not. Once it uh, detected the error in the transmission, it can ask for the retransmission. So the drawback of this is cannot correct, as well as it need an extra link to communicate that retransmission to the transmitter. Whereas in FEC, the receiver detects errors and also correct them. This method does not require a return link. So FEC obviously seems better than the error detection and retransmission. Whereas ARQ is a protocol that has different set of protocols based on uh, the retransmission, how much retransmission is requested, as it says automatic repeat request. So this repeat request is about the retransmission of the error near data. So the first type of ARQ is stop and wait ARQ that requires half duplexing. In that, we need to receive the acknowledgement for every transmitted packet, like shown in figure 6.7a. You can see transmitter transmitted first packet, received first packet, then there is an acknowledgement transmitted for that protocol, that packet. After receiving the acknowledgement, second packet was transmitted, and the process goes on. If, like you can see, packet 3 is transmitted, but received an error, so receiver will say NAK, not acknowledged. So it will be retransmitted again, and then it said acknowledged. Then the next packet will be transmitted as 4, and the process goes on. So you can see it's a slow process, and it need a lot of header information. On this acknowledgement information is the extra burden on the system, but it's reliable. You can say it's a foolproof, no data will be lost. Whereas in second one, continuous ARQ with pullback, it requires full duplex. You can see transmitter is transmitting its protocols, its packets 1, 2, 3, 4, 5, 6, 7 up to 10. Uh, Transmission is done to channel receiver. Now transmitting the acknowledgement, uh, delayed acknowledgement for the packets. So you can see there are three acknowledgement and then there is NAK. Uh, so that NAK received at while transmitting packet 8. So it will pull back to again 4. So you can see, so there was only need to transmit 4, but it will transmit all the packets again from 4. So that's why it's called pullback. Then continuous ARQ with selective repeat. It also requires full duplex link. So this one you can say the better substitute for the two other types, stop and with ARQ and continuous ARQ. Here you can see uh, there is a non-acknowledgement for packet 4 uh, at while transmitting packet 8. So transmitter receive this NAK. So it will only retransmit that particular packet, not all. So see, after 8, there is again a packet number 4 transmitted, and then it resumes its usual transmission from 9, 10, 11, 12, 13, 14, 15. Again, it receive a non-acknowledgement for packet 11. Then after 15, it will again has retransmitted packet 11. Then it resumes its usual transmission from 16, 17, 18. So how these error control codes works? Uh, Error control codes add redundant bits uh, to the message bits. So there is actual information that we say the message bits, and the extra bits that are the code bits are the redundant bits that are added with the message bit in order for the receiver to detect in case of ARQ or FEC. In case of ARQ is only detects. Okay, using those redundant bits, ARQ will be able to detect the error. In case of FEC, it will not only detect, but it will also can correct the errors using those redundant bits. So there are two categories of course, block course and convolutional course. A recent developed class of course is the turbo course that are based on the convolutional course. So we skip these general models because they are not that important. Um, so binary field and vector space. So binary number 0 and 1 together with modular 2 addition and multiplication form a finite field or Galileo's field. So we say that binary number 0 and 1 together with modular 2 addition like shown in table. This is modular 2 addition where when we have two same inputs like 0, 0, output is 0, 1, 1, output is 0. When we have different inputs 0 and 1 are 1 and 0, the output is 1. Similarly, in multiplication, all outputs are 0. Only when two inputs are high, we have the 1 as the output. Otherwise, output will be 0 in case of modulo 2 multiplication. So 0 and 1 together with modulo 2 addition and modulo 2 multiplication. This form a finite field or Galileo's fields. So this two here represents the this modulo 2 operation, multiplication as well as the addition, and this form the Galois field 2. So that will be used when we multiply or add the different binary number 0 and 1. So the properties of Galois field 2, under addition, the inverse element of 1 is 1. Since 1 plus 1 is equal to 0. So normally we say that 1 plus 1 is equal to, but in Galois field, 1 is the inverse of 1. So that is 1 minus 1 is equal to 0. So the inverse element of 1 is also 1. The inverse element of 0 is also 0, since 0 plus 0 is equal to 0. Under the multiplication, the inverse of 1 is also 1, since and 0, the inverse is not defined. Subtraction is defined as u minus v. That is, say it's u plus minus v, where minus v is the inverse of v under addition. Thus, 1 minus 1 is equal to 1 plus 1 is equal to 0. So vector space, the set of all binary n tuples v of n is called a vector space over Galois field 2. It is an n-dimensional space spanned by n linearly independent vectors. N tuples means like 3 tuples, 4 tuples, 5, 6 tuples. Like let's see, 3 tuples. 3 tuples means combination of 3 uh, bits. In that case, all binary n tuples will be, all binary 3 tuples will be tuple 0 from tuple 0 to tuple 1. So that will be 8. So that set of that set will be called Vn, and it is called a vector space over Galois field. So it will be an n-dimensional space spanned by n linearly independent vectors. So all vectors in that will be different from each other. Like you can see here from E naught to Vn minus 1. An addition of two vectors in Vn is defined by modulo 2 addition of corresponding elements, for example. So this is a 4 tuple. We have 4 bits here. 1001 plus 0101 is equal to triple 10. So 1 plus 0, 1, 0, 1, 1, 0, 0, 0, 0 should be 0. Yes. So there is a typo error. So 0, 0 is 0 and 1, 1 is equal also 0. So here it is 1, 1, 0, 0. So this should be 0. So scaling of vector is defined by the modulo 2 multiplication. For example, 1 multiplied with 1001, the output remain the same. If 0 is multiplied with the 1001 input, then output will be 0, all zeros. So in case of when you multiply with the 1, the output remain the same. When you multiply with the 0, the output will change to all zeros. So it also has distributive law and associative law properties. And then we have subspace. So that was the vector space. In subspace, a subset S of vector space Vn is a subspace when the following two conditions are satisfied. So the Vn is a larger vector space of total n tuples means we take the example of 3 tuples. In that it will be having 8 distinct vectors. So if you take few vectors from that vector space, we call that subspace. But that subspace, to say that portion a subspace, it must follow or it must satisfy these conditions, which are the all zeros vector is in S. So in vector space, we have a vector that is all zeros, and that should be in subspace to be that portion of that vector space to be called subspace. The sum of any two vectors in S is also in S. That is the closure property. That these are the conditions for to satisfy a portion, a subset of S vector space Vn to be called the subspace. Now it says let V1, V2, V of k, that is k is less than n. So n tuples, that is like for 3 tuples, there will be 8 vectors, and k like it will be less than the actual 8, means it will be consist on maybe 1, 2, 3, 4 vectors. So Vk vectors in a vector space Vn. So the total vector space is Vn based on n, and k is the vectors in the subspace. So the set of all linear combinations of forms a k-dimensional subspace of V of n. Only if it satisfy the previous two conditions. That is all zeros vector is in S. The sum of any two vectors in S is also in S. These properties are fundamental for the algebraic characterization of linear block codes. All code words of a linear block code form a subspace. So the idea of coding is to add n minus k redundant bits to messages of k bits. So from here you can see vector space and subspace concept is same as we have the n and k concept in the block codes. So the message will be consist on k bits, and we will add some redundant bits, then it will become total n bits. So k plus redundant bits is equal to total n bits. So n minus k will be equal to the redundant bits. So that means this k should be the subspace of this larger vector space. Then we can say that is the linear block code. So it says to add in linear block codes, the idea of coding is to add n minus k redundant bits to messages of k bits so that the resultant n tuples form a subspace. When received, if any of the code word is contaminated by noise or interference, it might change into another n tuple. If it falls outside the subspace, it can be detected. Of course, it might also become another code word. In that case, the error cannot be detected. See that point? We add some redundant bits, that is n minus k, to the actual message bit. So that become the resultant n tuple that form a subspace. So how we will detect that the received uh, vector is not in error? If it falls within the subspace of that n tuple, or it falls within the vector space, then we can say that it is not in error. If it is falls outside the subspace, then we will say that it's in error. Like let's suppose we have 3 tuples, and then we have 8 vectors. So that 8 vectors form a subspace. So, and we already know that their combinations are all zeros, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, and triple 1. So if any other combination other than this combination occurs, then we will say that falls outside the subspace. It might also possible that the error vector will be look like another vector in the subspace. In that case, we cannot detect the error. So example, a general formula is given here for the linear block codes, encoding of a linear block code. A linear block code can be generated by a generator matrix G, and where U is the code word and M is the uncoded message. For example, a code generator is G, and if the message is M, then the code word is 0 0 0 0 1 1 0 1. You can see that the first three bits, they all are different, or you can say they are from the they are the like subspace of a vector space of three tuples: 1 1 0 0 1 1 triple 1 1 0 1, and the 4 bits and the last 4 by 4 matrix, that is the unity matrix. See 1 triple 0 0 1 0 0. See, so when we multiply the 3 bits, these 3 bits are your redundant bits, and the last 4 bits are your message bits that remain the same: 1 1 0 1. Only the 3 bits will change accordingly. So note that modulo 2 addition and multiplication is used in this computation of the matrix. So when we do these multiplication and addition, we use the modulo 2 addition and multiplication. Now we see that a message of 4 bits is encoded into a code word of 7 bits. So we denote this code as 74 code. So total 7 and 4 is a message. So 3 redundant bits are added. N minus k, that will be equal to 3. Since there are 2 power 4 possible messages, because the input message consists on 4 bits. So 2 power 4 messages, possible messages. And there are 2 power 4 code words. Like you can see in table 3.1. That is 16. For all possible code words in 7.4 code, the set of all code words is called the code. In general, a message of k bits is encoded into a code word of 7 bits. Like you can see, if message is all zeros, then the code word will be all zeros. When message is 1 triple 0, then the code word is 1 1 0, and then the message is 1 triple 0, and so on. So now you can see this space that consists on 7 bits. That means it's a part of 7 tuple, but 7 tuple will have 2 power 7 total 128 128 vector space. So this subspace is called subspace of that vector space of total combinations of 128, because when we have 7 bits, the total combination will be of 1 to 8, and but we have this subspace. Now if any code word fall outside this subspace, then we will say that we have an error. If any code word falls within this subspace, then we cannot detect the error. It might be possible that the code word that is in an error looks like another code word available in the subspace. In that case, we will not be able to detect the error. So the general form of the generator matrix is G is equal to V1, that is the vector 1, vector 2, and to all vectors V of k, where these vectors are linearly independent row vectors, meaning any one of them cannot be expressed as a linear combination of the others. Thus, U is equal to M1 V1 plus M2 V2 plus M of K V of K. So that is a code word in the linear combination of generator vectors. The waiting numbers are the bits of the message. So the ratio K over N is called code rate. The ratio N minus K over K is called redundancy. These are these are 2 power K possible code words corresponding to all possible K bit messages. But there are total of 2 power N possible N tuples. Like in previous example, we saw that 2 power K was 4. So the total code words, possible code words will be 16, and total N tuples will be 128. So among them, only 2 power K are code words. So from a point of view of vector space, the 2 power n tuples form an n-dimensional vector space, and all the 2 power k code words form a k-dimensional subspace. So n produce a larger vector space, n-dimensional vectors, where k form only k-dimensional subspace. But all the code words, 2 power k code words will fall in the 2 power n vector space. So you can say that that subspace will be from that particular 2 power n vector space. Since the code words form a subspace, the sum of any two code words is another code word, that is a Caloe property, or more generally, a linear combination of any number of code words is still a code word. Thus, the name is linear block code. Another important property is that all zeros n tuple must be a code word in any linear block code. So like in the previous uh, example, in that you can see all zeros code words is also a code word. So and any addition between two code words is another code word. So that is a Caloe property. So this proves to be a subspace of the vector space because it satisfies the properties. Then we have systematic linear block codes. A systematic linear block code has a generator matrix of the following form: parity bits, and then we have the unity identity matrix, like this one. The eighth row is PI1, PI2, PIN minus K, and then we have the message bits, where the one is at position n minus K plus 1. Example, Q is equal M1, M2, M3, that is the message. And these are the parity bits, are the redundant bits. And then we have the identity matrix I3. So this is how you will have the uh, 2 power 6 code word message: U1, U2, U3, U4, U5, and U6. The last three bits are similar to that of the message bits. Because of the identity submatrix in the generator matrix, the bits in the second part of the code word are identical to the message bits, and the first n minus k bits are the return bits called parity check bit. With systematic generator, the complexity of encoder and the decoder are reduced. The P and IK submatrix matrices in the generator matrix exchange can extend position without affect the code's error detection and correction capability. If we express the code word as, then the relationship between the parity check bits and the message bits is as follows. So this is how you can relate parity and message bits. Then we have parity check matrix. The parity check matrix of a systematic code is defined as follows. Where H is like G is the generator matrix, then H is the parity check matrix. That is equal to I identity matrix n minus k, and then we have the transpose of the parity bits. And the transpose of H will be equal to n minus k and p, where the jth column can be given as like shown here. The first bits are the from the identity matrix, then we have the parity bits. So the multiplication of a generator matrix with the parity transpose of the parity check matrix will be equal to 0. That translate u h of t is equal to mg h of t, and when gh of t is 0, that will be equal to 0. So this is very important property that if we have a code word u, and if we multiply that code word with the transpose of the parity check matrix, then the output should be equal to 0 if that code word is a code word without error. So U is a code word generated by G if and only if UH transpose is equal to 0. Thus, we can use H to check whether a received N triple is a code word. So that is just to check whether the received code word U is a code word or not, is a valid code word or not. So we multiply that with the parity transpose of the parity check matrix. If it turns out 0, then we say that the received code word is a valid code word. That's called syndrome test and error detection. Denote the received n triple as R, let S is equal to R H of T. S is called syndrome. It is a vector of n minus k bits because H of T has n minus k columns. When S is equal to 0, R is a code word, otherwise R is not a code word. So this is how we determine whether the received vector is a code word, valid code word or not. Assuming a code word U is transmitted and when it is received, there are errors in it. These errors can be represented by an error pattern E, such that the received n triple is R is equal to U plus E. For example, U is equal to 110100 and R is 114001. Then the error pattern will be 001001. In fact, the error pattern is the difference between U and R. R E is equal to U minus R. Syndrome is computed as R H of T. If R is in error, then it will be U plus E H of T. And U multiplication with the transpose of the parity check matrix 0, the remaining thing we will have is E H of T. Thus, the syndrome only depends on the error pattern. The mapping between a correctable error pattern and a syndrome vector must be 1 to 1. This allows the correctable error patterns to be detected and corrected. If the error pattern happens to be the same as a code word, this error pattern will produce a 0 syndrome. Thus, the error pattern is not detectable. So example is given here. We have a generator matrix G, U is given, R is given, and error pattern is also given. So we calculate S is equal to R into H of T. So that is not equal to 0. It gives 011. So that means the received vector R is not the valid code word. It has the error. So what is the error pattern? That we determine by subtracting this received error pattern, that is 001, from a standard array and error correction table. One like this, like syndrome pattern. If syndrome pattern is 011, then the error pattern will be 40 then 10. So table like this will help us in fixing the error pattern and correcting the 1-bit error. So this is standard array and error correction similar to this one, where you can see we have this 00. Now this one bit will be included as the error like 001, 0010. You can see one is all the ways changing positions. Similarly here, it is 110100, and the one is moving. So in that, the first row is the code words. The first row is this one. These are the code words. The first column is the correctable error patterns. The first column is the correctable error patterns. So these are the correctable error patterns. So U1 is equal to U1 is all zeros vector, which is a code word and also an error pattern. And each row called a coset consists of an error pattern in the first column. And it's called the coset leader followed by code words perturbed by that error pattern. The array contains all possible entries in the vector space. None is missing and none is replicated. Example, the standard array for a 6-3 code shown here in this figure. So G will be given to you. You can make is H transpose, the standard array. So choosing the error pattern, use the error patterns with the least number of ones first in the 6-city code example. All 1-bit error patterns are used first. After exhausting all 1-bit patterns, there is still one position left. Then we choose the 2-bit error pattern. This 2-bit pattern must be from those 2-bit patterns that have not appeared in the array. In the example 01401 is chosen somewhat arbitrarily. The syndrome of a member of a closet is the same, like S is equal to UI plus EI. If you multiply with the parity check matrix, the first term U into H of T will become 0. The only remaining thing we will have the E of J into H of T. Note that each coset has a unique syndrome. A syndrome lookup table can be prepared for decoding. So this syndrome will give you the error pattern. So based on the syndrome value, you can determine what is the error pattern. Like here, all zeros, 001, like you can see the first column, that will show you the error pattern 001, 0010, 0010. After adding the error pattern in the code words, these all are the code words. How it look like that is given in the following columns, following rows basically. Like this is a particular code word 110100. So this is a code word. If this error is added in this code word, then it will be look like this 110101. If this error added in this particular code word, then it will be look like this. So the patterns after adding the error in the corrected code words, they are also given here. So that is, then we have the decoding procedure. First calculate the syndrome using this formula SR into H transpose. Look at the constant leader whose syndrome equals S. This error pattern is assumed to be corruption caused by the channel. The corrected received vector or code word is U is equal to R plus E. So we will add R again into E. Adding the error pattern to the receive vector is equivalent to subtracting the error pattern. Example is also given. Example U is equal to 101110 and the received is R 000110. So we first calculate the syndrome. We calculate a syndrome that is 100. So 100100. So 100 is there. The error pattern is this one. So the error pattern is determined. We will subtract that from the U from the receive vector. Receive vector is this one. Error pattern is determined. When you subtract this one from here, you will have the code word that is 101010, and that is same that was transmitted. So note that we do not have absolute certainty that the decoder output is what was transmitted, since there is possibility that the receive vector is the sum of another code word and another uncorrectable error pattern. So that is from the linear block course. Then we have error detecting and correcting capability. Uh, Hamming weight of a vector, that is W of U, that is the number of ones in the vector. Example, Hamming weight W of this particular vector tip 110100 is equal to 3 because it has 3 bits. So the weight of this code is 3. And the Hamming distance between the two vectors U and V, that is the number of components in which they differ. So one by one, first position 1 and 0. So they differ. First position is 1, second is 1. So they do not differ. We will not count. 0, 1, count 2. 1, 0, differ, count 3. 0, 1, count 4. 0, 0, do not count. So the difference between the two is 4. The Hamming distance between two vectors equals to the Hamming weight of their vector sum. So like this example, we say that the difference is the Hamming distance is 4. After adding U and V, we have weight also equal to 4 because it has 4 ones. So the minimum distance of a linear code, D minimum is equal to the smallest value of Hamming distances between the pair of code words in the code. If U and V are two code words in the linear code, then W is also a code word, since D is equal to distance between Hamming distance between U and V is equal to sum of U and V, its weight. So the minimum distance must be equal to minimum weight. That is G minimum is equal to W minimum, since all zeros vector must be a code word. The D minimum is the minimum distance between all zeros code word and all other code words. So how to determine the minimum distance? Method 1, find W minimum by inspecting all code words. This is feasible with small size code words with manual inspection. Is also feasible for big size with computer search. Method 2, use the parity check matrix H theorem. D minimum is equal to the minimum number of linearly dependent columns in the H matrix. So for any code word U and H, U H of t is equal to 0. If the code word has a minimum weight W minimum, then in the above sum, there are W minimum columns that add to 0. That is, there are W minimum columns that are linearly dependent. Thus, one can inspect the H matrix, find the least number of columns that add to 0. This number is equal to G minimum. So it says that like these are the columns. And if we add them and they turn out 0, this number is equal to G minimum. That is least number of columns. Like in this particular example, 63 code, any two columns add to non-zero. But we need a 0 column. We need a 0. Means if we add any two columns, like 1 and 2, so 1 plus 0, 1, that is 1, and that is 0. So that is that 0. So, but columns 1 to 4, when you add 1 to 4, that is 1, 0, 1, 1, 1, 0, 0, and this also 0. So that turns out 0. That means the D minimum will be equal to 3. Similarly, when we add 4, 5, 6, also add to 0. So the D minimum is 0. that we can determine from the parity check matrix H. Error detection capability. A code must detect errors in a code word before it can be corrected, or a code may be used for error detection only, such as an ARQ system. The error detection capability of a linear block code is equal to E D minimum minus 1. So if you know the D minimum, then you can know the how many errors it can correct. Since an error pattern of E or less non-zero component will not alter the transmitted code word to another one, such a code also is capable of detecting any error patterns with D minimum or more errors. In fact, it can detect any error pattern except for those that are identical to the 2 power k code words. That is the number of detectable error pattern is 2 power n minus 2 power k. For example, for 7-4 code, 2 power n minus 2 power k is equal to 112. The number of undetectable error pattern is only 16, a small fraction of the total error patterns. So that is from that lecture. Then we have cyclic codes. So cyclic codes are a subclass of linear block codes that is easy to encode and decode. Any cyclic, any cyclically shifted version of a cyclic code word is another code word. If you use a code word, then an n rounded cyclic shift is also a code word. So the name suggests cyclic code word. So if we change from u not un minus 1. So if you change it un minus 1 u naught, so that is another code word. If it is un minus I, so generally un minus I, un minus I plus 1 up to un minus I minus 1. That is obtained by I n around cyclic shifts is a code word. Like if we have 0 triple 1, that is a code word. Then you can turn around 1 to first, that is, then it will come 1 0 double 1 double 1 0 1 and triple 1 0. So that is how when you make a cycle of that, it will become another code word. So that is the property of that cyclic code. Its algebraic structure of cyclic code, the code polynomial of the its cyclic shift of a code word is a remainder of dividing xi by x power n plus 1. So that is polynomial division here. So u of x is the code word, multiply x of I and divided by x power n plus 1. The code polynomial of the edge cycle shift of a code word is the remainder of dividing this one n by x n plus 1. Proof is given, example is given here. Code word is 1101 code and the polynomial will become 10x plus x square. So 1 plus x. So this should be cube, not x square. This is 1 plus x. There is no x square. There is x cube. So this should be x cube. Then use the division method. We multiply with x square. This becomes x square plus x cube plus x power 5. And the remainder is x power 3, x power 2. So this is the another code word. That's read as there is no x power 0. So that is 0. X power 1 is 1, x power 2 is 1, and x power 3 is 1. So that is 0, double, triple 1. So the code word 1101 can be shifted to 0 triple 1. So that is another code word. So this is done through a division method. Generator polynomial of a cyclic code and NK cyclic code is best described by a generator polynomial g of x 1 plus g1 of x plus g2 x square plus up to x power n minus k. Note that g naught and gn minus k is always equal to 1. Then write the message as a polynomial m of x m naught plus m1 x m2 x square plus mk minus 1 x power k minus 1. The code word polynomial will be equal to multiplication of these two. U of x will be equal to m of x and g of x. And nk cyclic code generator polynomial g of x must be of degree n minus k and a factor of x power n plus 1. That is x power n plus 1 g of x h of x, where h of x is also a generator which generates an n minus k cyclic code. Example is given here. Uh, X power 7 plus 1 and g of x and h of x is also given. G of x will is equal to 1 plus x cube can generate 7 4 cycle code, and h of x can generate 7 power 7 3 cycle code. So for m is equal to 0 1 0 1, the code word is u of x m of x into g of x, where m of x into polynomial can be given as x plus x power 3, and g of x can be given as 1 plus x power cube, and the resultant is x plus x square x plus x power 3 plus x power 6. That is 0 1 1 0 0 1. That is the code word of the particular message 0101. So that is now the systematic. You can see, uh, unlike the linear block code where we have the messages and parity check bits are different from uh, each other. The following table shows all code was generated by the generator. Encoding in systematic form. In systematic form, we have to multiply uh, m of x first by x power n minus k. Then divide above by g of x. The result can be written as, where the remainder can be written as in the form of the p of x first, and then we have the message. Example we can see here. M is 1011. G of x is given. So to encode this in systematic form, we first multiply m of x with x power n minus k. X power n minus k is x power 3. So when we multiply, we have x power 3, x power 5 plus x power 7. Then we divide it by the generator polynomial, and the resultant is 1. That is x power 0 is 1. X power, there is no x power 1 and x power 2, so 0 0. So those are the parity bits 1 0 0, and then we have the message that is 1 0 1 1. Then we have polynomial divisor circuit. So we stop it here at 104A page number. So in your paper, linear block code and cyclic codes will be there. Cyclic codes, polynomial divisor circuit will not be there because we haven't covered it. So it will not be included. Uh, Similarly, this lecture will only have cover up to 104A. So simple cycle code will be, if there is any problem, it will be related to simple cycle code that we did it up to 104A. Nothing using polynomial division circuit. If you have questions, you can ask.
सर डीसीओ पेपर 23 ते आ वो तो उन हिसाब से अपलोड करी छॾिजो।
Sorry?
सर डीसीओ पेपर 23 ते आ पोइ फ्राइडे ते मे बी फ्राइडे थो लॻे त पोइ तव्हां उन हिसाब सां PDF अपलोड करे ॾिजो।
DCO paper 25 ते आहे?
23 ते सर।
DCO paper 23 ते आहे ऐं WCO paper 22 ते आहे न?
जी सर ईअं ई आहे।
ठीकु आहे, ऐं अपलोड करे छॾींदुमि, को मसइलो कोन्हे। हींअर ई अपलोड थो करे छॾियां मां, इहे जेके लेक्चर्स आहिनि PDF वारा जेके लेक्चर्स
ठीकु
आहिनि
आहे
न,
सर।
मां अपलोड करे थो छॾियां। तव्हां चओ पिया जेके फाइनल में ईंदा उहे लेक्चर्स तव्हां अपलोड करिया, ईअं?
जी सर।
ठीकु आहे, हा इनशाला सुभाणे ताईं करे छॾींदुमि। तव्हांजा सुवाल बुवाल हुते रखी छॾींदुमि, तव्हां पोइ ॾिसी वठियो।
ठीकु आहे सर, थैंक यू।
सर जीअं मिड में अपलोड कयो सर उअं ई कंदव?
मिड यार WC चेक कयो आहे ऐं DC चेक करायो पियो। मूंखे अहिड़ी जेका सो तबियत मुंहिंजी ख़राब थी, जेका सो जेका छा वञा टॉन्सल्स हूंदा आहिनि, मूंखे ॾाढो हिते टॉन्सल्स में ॾाढो सूर आहे। तव्हांखे लेक्चर ॾियां पियो न त मूंखे हिते जेका सो काफ़ी पेन थिए पियो। हा, उन जे करे मूंखां जेका सो वेठो ई कोन थो थिए, माना कापी चेक करण लाइ। इनशाला कंदुमि चेक, मुंहिंजी तबियत सही थिए इनशाला करियां थो। ॿुधाईंदुमि हुन में WC में सुठी आहिनि सभिनी मार्कूं, इनशाला DC में बि सभिनी सुठियूं हूंदियूं।
जी सर इंशाल्लाह
सर इंशाल्लाह।
सर इहो आउं चवां पियो त आउटलाइन सर अपलोड कंदव सर?
हा हा, आउटलाइन आउं रखंदुमि ते टीम्स ते इनशाला सुभाणे ताईं आउं ॿिन्ही सब्जेक्टनि जा रखी छॾींदुमि।
सर हल्की रखजो, पेपर गॾु ई आहिनि सभई, गैप कोन्हे को।
हा अल्लाह साईं ख़ैर करो, अल्लाह साईं ख़ैर करो।